So let's see Phasor diagrams for parallel AC circuits. In the last video, we saw the diagrams for series connections of elements in AC circuits. This time we're looking at the parallel arrangements. Let's start off with the RL parallel circuit. So let's say looking at RL parallel. So in this case, we have the inductor parallel with the resistor. Okay, so everything is connected to a particular source. We expect current to flow here, and then this is Vs as the case may be. Now, the Phasor diagram will look somewhat like opposite of what we have for the series RL circuit. In that case, our voltage, of course, is in phase with current, but this time we draw this way. Okay, this is Vs, which is in line with our VR because they are in phase. And now this is the value for our I now. So like we said, voltage leads current, but at a particular angle for parallel arrangement. So unlike for our series connection where we are looking at the movement of voltage, this place we are looking at the movement of current, because for series connection we already know that current is constant while voltage is the one varying. But for parallel arrangement, it is the voltage that is constant and current is varying. So the current is moving following the voltage. So voltage is still leading current in this case, but at a particular angle. We all know that pure inductance and pure capacitance, that current is always in phase with voltage. So here we have the current flowing in the system I is lagging behind the voltage, and here is the current flowing through the inductor IL. So this is the arrangement we have for parallel combination of what RL circuit, where this is L and this is our R. I hope this is clear. It is worthy to mention here that current flowing through the inductor IL is in quadrangle with the words IR. That means it's at 90 degrees with IR. So current flowing through the resistor, they are what 90 degrees out of phase. So the resultant current is seen, which is here, the resultant current is seen to lag behind the applied voltage Vs. And the magnitude here we can get it from what I, which is the current here, is the same thing as what IR square plus what IL square. And we can actually prove that from Pythagoras here. Okay, this I here is hypotenuse, and this is IL, and this is IR. So the square of these two sides should be equal to the square of I. Okay, so that said, we now know the value for our magnitude, which is the current flowing through the system here. And with that, we can get the value for our phase angle, the angle of lead or lag, which can actually be seen from the relationship between I and what R. Okay, IL and IR. So and the relationship can be gotten from tan, of course, where our phi can be what the tan inverse of IL over what IR. Alright, so let's look at the Phasor diagram for RC parallel circuit. In this case, we have capacitor connected with resistor in parallel. So we're going to see the graph. The graph also is going to look just like opposite of what we have for RC in series connection. So what we have here is our current leading voltage, just like we've stated earlier. Current will be leading voltage. So here we have IC and this is VS. And in this case, we'll also see, just like we explained for the pure inductance connected in parallel with resistor, that's what the current here flowing through IC is leading the current flowing through RL by 90 degrees. So we know that our IR is in phase with the voltage. So the current here is leading by 90 degrees. But the current, the magnitude, that is the resultant current flowing to the system I, is what going to lead voltage by a angle called phase. And from this, we can also get the formula for our magnitude, which is the same thing as what we had for the RL circuit. So magnitude is still going to be the same thing as what IR square plus IC square, where we can see from Pythagoras that the square of this is something as this addition of the square of the other two sides. So with that, we can also see that our phi can be gotten from tan inverse of what IC all over IR, which power factor can also be seen to be the cos, and power factor can be seen as the cos of what I R all over what I, as you can see here, cos theta cos phi is the same thing as what opposite over what hypotenuse, and that will be the expression for parallel RC circuit. I will show you for the combination of RC and L, and then we go into the examples where we have the connections in parallel. If you have a RLC circuit connected in parallel, how do we go about the phasor diagram? We can see in different cases where our XC, for example, is greater than SL, is going to, the graph will look differently from when our XL is greater than what XC. That means the inductance is greater than capacitance. The graph will look a particular way, and when is vice versa, it will look a different way. So let's look at instance where inductance is greater than capacitance. So case one where XL is greater than XC. So the graph will look simply like this. Of course, we know this is our VS, and our IR is in phase with VS because it's pure resistance. So since SL is greater than XC, that means our IL will be greater than IC. So in this case, the resultant current, therefore, will be I, as we all know, and then the angle here is phi, which is the angle of lead or lag in this case. So with this, we know that we can actually substitute the values for IC and IR in what we had earlier. So our resultant current will look somewhat like IR square plus, here we now have IL minus what IC square, and the root of it should give us the value for our current. Of course, the phase can always be gotten from tan inverse of IL minus IC all over IR. And that is basically what it is. So if by peradventure it is our SC that is greater than SL, in that case the graph will take the other turn with our value yet being IC minus IL, and the graph comes this way. This becomes our phase angle, and everything remains the same with I here, except that in place of L here we have C, and in place of C here we have L. So the formula will become somewhat I square R plus IC minus IL square is got our I, and the tan inverse of IC minus IL over IR becomes the value for our phi. So that said, that is what you should expect when we have all the connection in parallel. But in some cases, which is obviously a special case where the value of our SC is the same thing as SL, which is the case where we call resonance. In the next video, I'm going to show you these special cases. But